Okay, let's go for example 4.2. Okay, so let's go for a reduced shaft as shown below, subject to a fluctuating torque. Okay, of 1,500. 2 minus 1,500 is made of 1050 HR steel. Given that the surface is made of machine, surface of Ka is 0.73. The safety factor is 2. Determine the current shaft diameter. So let's have a look together at the figure there. We have a load of torque applied from the head to toe from A, B, C, and D shaft respectively. And we have band to support at A and D respectively. So therefore, in conclusion, we have only a single load acting on it. So therefore, we have a load on it. So therefore, we gonna experiencing a stressed. Okay, just experience it inside the workpiece. There is going to be look like to me. It's going to be tau going to be equal to torque time R over J, and then this shaft is rotating. Of course, this kind of thing is going to be rotating, and then since the torque here is going to go back and forth, so minus and plus respectively. So therefore, this gonna cause this kind of shaft to be a fatigue design, of course, right? So therefore, are there any stress concentration? Of course, there is at B and C. So I'm gonna determine which points it's gonna be the things I wanna go put on the design. Either gonna be at B or C. KT at B or KT at C, which gonna be U higher. I'm gonna make a determination first. So therefore, in conclusion, I find thing first. Okay. For the steel as given by the problem set, I find sigma y and sigma u form the appendix number 1. I got to find tau sub y equal to 2.04, okay, 204 respectively. And sigma u is 60620. I find the sigma n respectively, and then I can find the k sub a, and then I assume, see, be careful here. I assume d is going to be greater than 50. Typically, I don't do this. D is in between 8 to 50, as what I mentioned earlier. But this kind of thing, I guess it's going to be like this. Okay, I assume to be like this. And then, see, this one is going to be under torsion all the way. K sub C is this. So therefore, this is going to be the shear stress alone. So therefore, the tau sub n going to be replaced in here. And then since I mentioned earlier the stress concentration is only happening here at B and C, I'm going to determine either the design going to be at B or C since there is only stress concentration under the shear stress only. So therefore I find the D over D, okay, at point B and R over D at point D, and by point B I find the KTS, okay, at point B. And point C, also I find the KTF is going to be 1.2. So therefore, no doubt about it, the point B is going to be greater than point C. The design just must carry on at point B, okay, with the KT sub S is going to 1.25. Okay, so the design should be done at B. So everything is going to brainstorm at point B in conclusion. So I find the torque and everything's at B respectively. So therefore, the torque mean at point B is going to be 0. And the torque amplitude is going to be 5, 1,500. I find the tau mean and the tau amplitude respectively. I plug it in. I plug it in, the Soderberg criteria. I got a diameter of 557.24. I'm lucky, right? I'm lucky because that's why I just assume to be greater than 50. Okay? So if not, I got to repeat it one more time again. This is the design that what I got the lucky answer. Everything's gonna be automatically answered. Okay. So now I'm gonna go for the fatigue design under the fluctuating and combined loading. So everything's gonna go together. That's what I mean by combined loading. Everything's gonna come together, not either. Okay, simple stress is going to come up with the normal stress, bending stress, everything's going to come together. Okay, so therefore we're going to use the failure theory, sort of a criterion together. So therefore everything's going to come together. We modified everything together, we're going to have equation 455. which is 1 over n, and the tau is going to be tau EQ, equivalent shear stress, and then sigma equal equivalent normal stress, respectively, for the equation 455. And then equation 456 is going to be sigma EQ and the tau EQ, respectively. Be careful. 4.6, we're going to have KT, and 4.7, we're going to have a KT sub S, KK sub TS, respectively, only. See? And then we're going to apply either maximum shear stress theory and octahedral shear stress theory, respectively, whatever you want to. Okay? But typically, what I mentioned earlier, the maximum shearing stress theory is going to be most popular anyway. So therefore, okay, let's see the example. It says here, a reduced shaft as shown below, subject to a constant torque of 1,500 and a reverse loading of F is 2 kilonewton and made of 1050 steel. It's given the surface is machine surface. And then the safety factor is 2 using the Soderberg and the maximum shear stress theory together to solve for the problem. Okay, let's see together here. Okay, I have the two loads. One is going to be F towards loading, and second is going to be the torque. Okay, it's constant all the way. So therefore, this one, the torque here gonna cause the tau, right? Tau is equal to torque times R over J. So one is going to be the shear stress, and the second is going to be the F there. F here is going to be course the bending. Okay, it's going to be sigma equal to m times c over I. Okay, so therefore it seems to me if the shaft is stand still, okay, it's going to cause some kind of like static design. But this one, since the shaft is moving, so therefore it's going to cause a real reverse bending. So therefore it's going to put some kind of like reverse bending. So it's going to design like a fatigue design then. So we're going to put the design right there at any particular stress concentration area. Stress concentration area is going to be right there at B, either B or C then. Okay, we're going to determine either B or C is going to be greater then. Okay, so therefore automatically I got to find the moment right there at B, either B or C then. Okay, as a reference. So therefore things like that. Okay, I just do the first thing first, the design area then. Okay, I find the K sub T, K sub TS right there first. So I found it at point B. I find at point B KT and KTS there, and at point C KT and KTS right there. So in conclusion, you may figure out there. So you said point B is greater. So no doubt about it. I got design there at point B. Okay, and from now on, I keep in mind, okay, everything gonna be signed at point B. So with KT is 1.45 and KTS is gonna be 1.25 respectively. Okay, with the corresponding moments, it's gonna be right there. So therefore, okay, I got the material sigma y, sigma u, and I got sigma n prime. I got machine surface. I got d is greater than 50. I got kc there. So therefore, I got the tau sub y. I use the maximum shear stress theory. I got tau sub n, and then the torque max is got the torque mean. It's got 1,500. I got the torque means and the top amplitude. I got the tau amplitude and tau mean respectively, and then I got the tau equivalent. I plug it in there. Okay, and then this one, the shaft is subject to troubleshooting of F is equal to 2. Apply inversion techniques by rotating a transverse force of F around the fixed shaft. Therefore, the bending moment is equal to minus moment minimum. So therefore, at moment is B, because that's why we just figure out the design should be done at B, right? So therefore, this one moment max is equal to minus moment min, right? So the moment min is equal to 0. Okay, moment amplitude is equal to 163, things like that. Average is equal to 0. The amplitude is equal to this. So the sigma equivalent is going to be this. And then, so that's why I plug it in. the Soderberg equation, I got the answer of 45. Since we just assume that, see, this one, d is greater than 50, so that's why we got to make a recalculation from the beginning. So therefore, we just repeat it there. So everything's gonna be just repeated. I got the correct answer. So I got the answer there. That's correct manner. Okay. So another one, fatigue, stress, concentration factor to the keyway. So that what I mentioned earlier. See, when we just have a child, we're gonna fix the keyways. Okay, we gotta fix the pulley. Okay, on the keyways look like that. Okay, so it's gonna be look like that. See, we have a shaft, and then we put a pulley there, and we have a hub. We have a hub here, and then we put a hub on the shaft. So that's why we're gonna put a keyway there, and we put a key inside there. So therefore, we're gonna hurt there for the shaft there. So therefore, in order to do on that, we're gonna cut the shaft look like that. We have two methods to do on it anyway. One we call it the slit liner. It's gonna be like that. See, and second we're gonna use the profile keyway look like that. See, so slit liner we're gonna use some kind like hopping machine. Okay, I'm sorry. We're gonna use some kind like hopping machine to make some kind like do the profile keyway, things like that. I'm sorry, do the slit liner keyways, and then for the profile keyway, we're gonna use the some kind like machines look like that. Okay, to round it up. Okay, to cut it. Okay, so therefore, this kind of thing is going to be two things that what you make on it. Okay, this is going to be the slit liner and then the profile keyway. You're going to use it, but simply, mostly, okay, the slit liner, okay, we're going to use this kind of shaping machine to do on it anyway. Shaping machine is mean we just hold the workpiece and then we just use the uh, shaping machine to cut it along the length, things like that. Okay, and then profile we use a milling machine to cut it. This is gonna rotate around, so therefore the profile keyway gonna look like that. See, lower the value is gonna be better. Okay, so this kind of thing is gonna be better. So therefore, see, this is gonna be the thing that show you up there. Anode steel HR, and then the cordon steel is gonna be look like that. See, so typically the HR steel, okay, and then the cordon steel is gonna be under that. Okay, so therefore you may see the qualities of the KT, okay, the bending, okay, is lower. Even than KTS is going to be lower if you compare between these two and one. Okay, so therefore, this is going to be of example 4.4. As to show you, a solid shaft is made of 1020 CD steel having a machine surface, okay, and uses transfer power from the engine by using a belt pulley to the clutch as shown. The pulley weight of 1,400 is mounted on the shaft with key. The shaft is cut with a profile keyway. The belt tension are 1,200 and 200 respectively. Determine the shaft diameter by using the solid cut tune together with the maximum shear stress failure theory using the safety factor of 2. Okay, so let's see together here. Okay, we have a bearing there, we have bearing A here and bearing B there. We have a pulley there, and the tension on this side 1,200. Another one loose side 200 there. Everything is going to pull down together, so therefore it's going to have a total force pulling down. It's going to be 1,200 plus 200, and we have another weight, okay, of the pulley itself. It's going to be another 1,400 respectively. We have a torque of 1,200 minus 200. So therefore, okay, so we have a keyway, we're going to have a stress concentration on the shaft. Okay, so therefore, let's follow this. Since the key have to be cut in the shaft, therefore the design has to be take the stress concentration and the keyway into the consideration. The failure may occur at the high stress concentration point at the keyway. Therefore, the design have to be done at this point. So therefore, it's going to be right there, design point. Okay. So therefore, okay, the appendix one there. Okay, we got the material there, the shaft, sigma y, sigma u. Okay, we got a routine there, sigma u, and then we have a sigma n, we have ka, kb, kc respectively, and then we have a tau sub y, tau sub n respectively, tau max, tau min, we have tau max, tau min respectively, and then we have torque, and then we have tau amplitude and tau mean respectively. And then based on table 4.1, we have a material of 1020 CD steel, right? The CD steel, so therefore the CD steel there, so therefore we have the given by the problem set is gonna be cut with what the profile keyway, right? Profile keyway. So therefore CD steel and the profile keyway. So therefore KT is gonna be 2.0 and KTS is gonna be 1.6 respectively. So therefore based on this, I have the KTS 1.6. Okay, and then for the loading of F, there 1,200 plus 200, 1 plus another 400. Okay, so I got the maximum and max minus and min, things like that. I got 140 meter. I got therefore the sigma is going to be there, and I got KT, and I plug in the Soderberg equation there. So therefore, I got the answer around 34. So therefore, the shaft there, I make a calculation is correct one. Anyway, see, then the example 4.5 is very useful. Okay, I used to take this kind of thing as an exam before. Example 4.5. Please have a look at it. Okay, I just make some kind of like the equation to be with the two axes anyway. Okay, vertical axis and horizontal axis anyway. So for the determination. Okay, so please everybody, and then example 4.6 also I used to put this kind of thing as exam before we have a look at it 4.6. Okay, and then okay, so please have a look at it. Okay, and then I would like you to do some homework for me. Okay, number one there. Okay, please have look at it. Okay, and then do the homework for me and submit it to me. Okay, number one there. Okay, and then number five there, please. Okay, okay, number five there. Okay, that's just it. Okay, for this chapter. Okay, thank you. Okay, that's it for the chapter then. Okay.